constant velocity. So the basis for this experiment was Newton's first and second law. So Newton's first law states that an object at rest tends to remain at rest, and an object in motion tends to remain in motion unless acted on by an outside force. So in other words, if there is no net force, then velocity will remain constant. And this is proven by the following equation, which can be derived from Newton's second law. So the equation is velocity final equals velocity initial plus F net over mass times the change in time. So if we made F net equal to 0, this means that everything after the plus sign, so everything after the velocity initial, would be 0. So this will leave you with velocity final equal to velocity initial, which shows that velocity remains constant whenever you have 0 net force. So for the experiment setup, so to prove the concept of constant velocity, I rode a basketball in a straight line right outside my dorm. I then tracked the motion of the basketball using the tracker application, which automatically rendered a position versus time graph. And using this graph and its data, I was able to determine the velocity of the basketball using the following formula, which is V average is equal to displacement over the change in time. And you're going to see more about that on the next slide. So these are my observations using tracker. So I used the initial x position as negative 2.827 times 10 to the negative third meters, very close to 0, and the final x position of negative 9.465 times 10 to the negative 2 meters, which is also very close to 0. And I did this over the time interval of 0.067 seconds. And I was able to compute the velocity of the ball to be negative 1.3705 meters per second. And I used this velocity also in my computational model. And again, I used the formula V average is equal to displacement over the change in time. And these data points can be visualized using tracker, as you can see on the picture on the right. So what if the axis was changed? So initially, the ball rolled in the negative x direction for this experiment, but if we changed it so the ball rolled to the positive x direction, the speed would stay the same, right? Because speed is a scalar and direction doesn't matter for speed, but velocity would have been different because for velocity, direction does matter. So if the axis was changed, speed would remain the same. However, the velocity would change because for velocity, the direction matters. So this is my code for the initial conditions. So ball.pos is equal to a vector negative 0.002827, and this represents the initial position of the ball. And then ball.vel represents the velocity of the ball, which is negative 1.3705 meters per second. And this will remain constant throughout the model because we are testing constant velocity. And this was the code for the this was the code for the actual simulation. And I used a while loop, and I set it to run while time was less than 1.367 seconds. And this is because that was the time of my last observation. And also included the velocity update formula and the position update formula so that a graph could be made using those formulas. And this is what I got. So this is the model versus experiment graph. The red line is the model position, while the blue dots is the experiment position. And as you can see, the experiment position and the model position lined up well in the beginning. However, towards the end, the model position started to veer off. And this could be attributed to two things. First, there could be an error in the tracking points on tracker. And secondly, the computational model did not account for friction force. So this is why the computational model is just linear, while the experiment position, it kind of starts to slow down because of that friction force. So we had to make some main assumptions for the model to kind of make it go smoothly. So firstly, we assumed that F net was 0, therefore friction force was not accounted for. And we also did not account for the first frames where the ball was speeding up and the last frames where the ball started to slow down because of that friction force. And you can see that on the code snippet on the right where we set F net equal to 0. So what does zero net force actually represent? We use zero net force as the basis for the experiment. So what does it actually mean? So zero net force means that velocity will remain constant. So in the case of the rolling ball, we assume that there's an equal amount of push and pull, which makes it zero net force. And you can see this on the picture on the right where you have the same amount of force to the left and the same amount of force to the right, so net force is 0. In reality, however, because of friction, there is a bigger force to the right, which ultimately causes the ball to slow down. So that was the end of my presentation. I hope it was informative, and thank you.